Okay, so welcome to this next video in the playlist on metabolism. In this video, what we're going to talk about is glycolysis, which is the first portion of the respiratory reactions. Okay, so we're going to talk about glycolysis. Okay, so glycolysis takes glucose and it converts it into pyruvic acid molecules. Now, just before we start discussing the glycolytic pathway, I want to begin with a discussion of what the difference between a pyruvic acid molecule and a pyruvate molecule is, because we will see this all over the place basically when we discuss this pathway. We'll see, for instance, glycerate and glyceric acid, okay, and we want to know what the difference between them is. Okay, so it's all over the place and it's a very general principle from chemistry. So, let me draw you out the structure of pyruvic acid, which we'll see later. Okay, so pyruvic acid is a free carbon carboxylic acid. Okay, so you have this carbonyl group in the middle, then you have a carboxylic acid group over here, and then on this side you just have a methyl group, so a carbon with free hydrogens coming off it. Okay, so the structure that I have drawn you there is strictly speaking called pyruvic acid, okay? However, if I actually made a solution of this, if I got loads of these molecules and put them into water, would they all stay in this exact same form? Well, no, because this is an acid. Basically, it means that this proton here on the alcohol group of the carboxylic acid group, that isn't very stably attached onto this oxygen, and it can fall off basically and go into the solution. Okay, so that's why this is called an acid molecule. And when that proton falls off, what are you left with? Well, the remainder of the molecule looks like so. So here's the methyl group, unchanged. Here is the carbonyl group, again unchanged, but now the carboxylic acid group now no longer has that proton, and instead the oxygen has a negative charge. Strictly speaking, this molecule is now called pyruvate. Okay, so pyruvate is pyruvic acid once it has lost its proton, basically. Now, there is a fancy name for this, because this works not just for pyruvic acid, it works for any acid you can think of. Any acid can lose its proton and then it has another molecule which can be given another name, and they usually end in ates like this. Okay, so this is what is known as the conjugate base of the acid. Now, the reason it's called that is because this molecule actually is no longer an acid, but instead is a base. Because if you think about what the definitions of acid and bases are, an acid is a molecule which can donate protons away, such as this molecule here. Pyruvic acid can donate protons away, okay? Whereas this molecule, it can't donate protons away anymore. Where would it donate the proton from? Instead, it can actually receive protons because it has a negatively charged oxygen here, and protons can come and join here to re-synthesize the pyruvic acid. Okay, so the reaction goes both ways, basically. And therefore, this molecule is actually a base. So it's called the conjugate base of the acid, basically. And all acids will have a conjugate base, and often they have a different name for the conjugate base than the acid, basically. So, whenever people talk about pyruvic acid, it's okay just to say pyruvate, because in reality, if you have a container here, and you have loads of pyruvic acid molecules in solution, then there'll be an equilibrium with their conjugate base pyruvate, so you can't just have pyruvic acid. You also must have pyruvate, so you'll have a mixture of pyruvic acid molecules and pyruvate. You can't just get pure pyruvic acid, because as soon as you put them in there, they'll start donating their protons away and producing you pyruvate. That's why people use these two words interchangeably. Most people refer to the conjugate base rather than the actual acid. So often people will just call it pyruvate rather than pyruvic acid, but they are effectively interchangeable, because whenever you have one, you will also have the other, and there'll be an equilibrium, a dynamic equilibrium. Okay, so that we're going to see this conjugate base terminology all over the place, basically, and really you can just use the two words interchangeably. Okay, so let's begin then with the process of glycolysis. I thought it was important to go over that to save us time later. Okay, so we're going to begin with glucose. Now, glucose is a far more tricky molecule than people appreciate. It has many different optical isomers. The major form of glucose that people usually mean when they just say glucose is what's known as alpha-D glucopyranose. Okay, so the full name for what people usually mean when they say glucose is alpha-D glucopyranose. So let me show you the structure of alpha-D glucopyranose. So firstly, what I should say is that glucose can exist as a linear molecule. It doesn't usually exist as a linear molecule within cells. It usually exists as a cyclic molecule, but actually, when you really say glucose, strictly speaking, what you should be talking about is the linear molecule. If you mean the cyclic molecule, which is the form that is mainly present within cells, strictly speaking, you should call that glucopyranose. Okay, so let me show you the structure of the glucopyranose. Okay, so it's a six-membered ring like so, and we'll draw a skeletal structure, or at least it'll be close to a skeletal structure. And you have an oxygen up here, and then the other 5 members are carbons. Okay, so this is the cyclic form. It's in a ring structure, not as a linear form. However, it can exist as a linear form, and strictly speaking, if you just say glucose, that should refer to the linear form rather than the cyclic form. Okay, now there are also many different optical isomers of glucopyranose. So when glucose is in this cyclic form, there exist many different optical isomers. Now, even in the linear form, there are 2 optical isomers, D-glucose and L-glucose. But when you cyclize it, there's another scope for optical isomerism, and this creates the alpha-beta. So, basically, the D here refers to the fact that the 6th carbon comes out of the page towards us. So if you imagine that this 6-membered ring here, where we have these 5 carbons and this 1 oxygen, if you imagine that this is present within the plane, then the other 2 bonds that are going to come off each one of these 5 carbons here, one will come out of the page towards us and the other will go into the page away from us. Now this D-glucopyranose, this means that this 6th carbon here is going to come out of the page towards us. Okay, so I'll draw it like so. I'll colour in this little bond here, okay? And then you have a 6th carbon here, and we were doing skeletal structures, but we'll just break with that for a moment. And then off this 6th carbon, you then have 2 hydrogens and an alcohol group. Okay, so basically, this then implies that the other group which comes off this 5th carbon here is going to go into the page away from us, and that's just a hydrogen. Okay, so when you put the D there, that means that this 6th carbon comes out of the page towards us and the hydrogen goes into the page away from us. If instead you put an L there, it would mean that this 6th carbon went into the page away from us and the hydrogen came out of the page towards us. L-glucopyranose is not present in any respectable level within cells, so that's why we don't usually acknowledge even that that exists really in biochemistry. It's something that chemists can make, you know, but it's not something that is within cells. Right, now, the optical isomerism of this carbon's groups, and this carbon's groups are absolutely set. The instant you talk about glucose, those are set, okay? So each one of these carbons has an alcohol group coming off it and also a hydrogen molecule, atom coming off it, okay? And basically, you have to decide whether you want the alcohol group to go into the page away from us and the hydrogen to come out of the page towards us, or if you want the hydrogen to go into the page away from us and the alcohol group to come out of the page towards us. Now, in glucose, this is set. So the alcohol group goes into the page away from us off this 4th carbon. Then the alcohol group comes out of the page towards us on this third carbon over here. Okay, and the hydrogen therefore goes into the page away from us. And then finally on the second carbon, the alcohol group goes into the page away from us. If you change the optical isomerism here, i.e. you swap the alcohol groups and the hydrogens around, then what you have is no longer considered gluco. You would have to change this here to mannose or another one of the aldohexoses. Okay, so don't mess around with those basically. Those thankfully are actually set. Now, there is also the question of whether the alcohol group that comes off this first carbon and the hydrogen atom that also comes off here, either you can have the alcohol group coming out of the page towards us and the hydrogen going into the page away from us, or you can have it the other way around. The alcohol group goes into the page away from us and the hydrogen comes out of the page towards us. Okay, now this is what this alpha refers to. If you are talking about the alpha isomer, it goes into the page away from us, okay? And these two types of isomer are known as the anomers, okay? And I'll explain this in a bit more detail. So if the alcohol group off this first carbon goes into the page away from us, then we are talking about the alpha anomer of D-glucopyranose, okay? And the reason it's called this is that this first carbon here, which I've now highlighted in turquoise, this is called the anomeric carbon. Okay, so the optical isomerism around this anomeric carbon determines which anomer you're talking about. So we've set whether we're talking about D-glucopyranose or L-glucopyranose. We now have to decide upon which anomer we're talking about. So we're talking about D-glucopyranose, and either you can have the alpha anomer, where the alcohol group goes into the page away from us, or there's also the beta anomer, and beta glucose is biologically important. Okay, so it shouldn't be neglected like we neglected the L type of glucose. Okay, so in the beta anomer, the alcohol group would come out of the page towards us. So you do find in biological systems alpha D-glucopyranose and beta D-glucopyranose, but you don't find alpha L-glucopyranose and you don't find beta L-glucopyranose. So there are overall 4 optical isomers of glucose: alpha D-glucopyranose, beta D-glucopyranose, alpha L-glucopyranose, and beta L-glucopyranose. And we find the alpha D and the beta D, but we don't find the alpha L and the beta L in nature. Okay, right. So the form of glucose that we are going to be concerned with for respiratory reactions, for glycolysis, is this alpha D-glucopyranose. So as I say, glucose usually exists in the cyclic form in cells. And I should just add that if it's not in the cyclic form, you don't actually have to worry about the optical isomerism of this anomeric carbon. It isn't actually a chiral center in the linear form, so you only therefore have 2 optical isomers of the linear form of glucose. You have D-glucose and L-glucose, so that's quite interesting. But as I say, the linear form doesn't really exist in cells that much. The cyclic form is the main form. So, strictly speaking, you should call this form of glucose that I have drawn out, you should call it alpha D-glucopyranose. But everyone knows that you're talking about that, or at least they should, and therefore people just call this glucose. This is the major form of glucose that is within cells. Okay, so we are going to start with this alpha D-glucopyranose, and this is what we're going to use in the respiratory reactions. Okay, so let's now look at the first reaction in the glycolytic pathway. So the first reaction is a non-reversible reaction. Okay, so this is a one-directional reaction, and this is going to be important when we come on to discuss gluconeogenesis, because this means that we're going to have some way of circumventing this irreversible reaction. Okay, so this reaction can be catalyzed by one of 2 enzymes. So there are 2 enzymes which catalyze this reaction. One is known as hexokinase, which is present famously in skeletal muscle, and the other is known as glucokinase, which is present within hepatocytes and pancreatic beta cells significantly. So either one of these enzymes will catalyze this reaction. Okay, and what we're going to do is we're going to add a phosphate group onto the alcohol group that comes off the 6th carbon of the alpha-D glucopyranose molecule, or what from now on we'll just refer to as the glucose molecule. Okay, so where are we going to get this phosphate group from? Well, we're going to get it from ATP, okay? And I just want to add another little piece of terminology. The first stage of glycolysis that we're going to look at is what's known as the preparatory phase, okay? So this is the phase where you prepare to get a payoff, basically, but you're not actually going to get a payoff. It's also sometimes called the investment phase, because actually we are going to invest some ATP into the process, which seems odd, because, you know, glycolysis is about generating ATP, but we're actually going to use ATP in this first stage of glycolysis. So in fact, we're going to put 2 ATP molecules in the preparatory phase of glycolysis, and then later off in the payoff phase, we're going to get 4 ATP molecules out. So we double, basically, our ATP molecules in the process of glycolysis. So the payoff was worthwhile for the investment that we made. Okay, so this is an example of where we're going to invest ATP. We are going to take this phosphate group from an ATP molecule and reduce it down to an ADP molecule. So let me just draw little cartoons of ATP and ADP to try and explain what's going to happen, basically. So basically, if we draw a little cartoon of adenosine triphosphate, I'm not sure it's going to fit in here, but never mind, I'll have a go. Okay, so here is the ribose molecule. Here is the 5th carbon of ribose. And then you have the organic base adenine. Now, when you have the organic base adenine linked to ribose, that's known as adenosine. Okay, so adenosine is the name for adenine linked to ribose. So we've got an adenosine molecule here. So I'll just colour it in. And so here in blue is the ribose molecule, and we'll have in pink the organic base molecule, which is adenine. Link the 2 together and we've got adenosine. Now what we will have is a few phosphate groups stuck to this to create adenosine triphosphate, ATP. And we'll have 3 phosphate groups because it's triphosphate. Okay, now what we're going to do is cut off this final phosphate group, and they're basically labelled, so let me just colour in the phosphate groups. So the 3 phosphate groups of an adenosine triphosphate molecule are labelled the alpha phosphate group, the beta phosphate group, and the gamma phosphate group. Now what we're going to do is chop off the gamma phosphate group from the beta phosphate group and add it onto this 6th carbon of the glucose molecule. Okay, and that will take us down to ADP, because we'll now have adenosine with 2 phosphate groups, the alpha and the beta phosphate group, but without the 3rd phosphate group. Okay, so let's see how this affects the glucose molecule. So I'll draw the glucose molecule again. So we've still got our 6-membered ring here. Okay, I'll just move this up a little bit. Right. So 5 carbons in this ring and then 1 oxygen. And now I'm going to change my notation a little bit, because I absolutely hate drawing out these silly sort of bonds that get thicker towards the end. It takes too much time. So instead, where I'm going to denote whether it's coming out of the page towards us or into the page away from us is if I draw the bond coming up off this carbon, that means it's coming out of the page towards us. And if I draw the bond going down at the carbon, that means it's going into the page away from us. This is a common trick people use to get out of having to draw these difficult bonds, basically. So let's just finish this optical isomerism off before we discuss the addition of the phosphate group, just so that we're sure we have the notation sorted. So this is coming out of the page towards us, so I draw the bond coming up. Okay, so there it goes. This one's going into the page away from us, so I draw the bond going down. Okay, this one's going into the page away from us, so again I draw the bond going down. And this one's coming out of the page towards us, so I draw the bond going up. Okay, I then have an alcohol group coming off this carbon, and I'm adhering to the skeletal structure now and not drawing the hydrogens coming off that carbon. And now what will happen is it will have a phosphate group linked onto it here. Okay, like so. Right, okay, and I'm just going to discuss with you what the structure of an inorganic phosphate group is, or a pure phosphate group. So let me discuss inorganic phosphate. Okay, and inorganic phosphate is often abbreviated to PI because we'll see inorganic phosphate groups later on in this video. So I think it's worthwhile just discussing what the structure of a pure phosphate group is, and then how really this is a phosphate group linked onto that alcohol group of the 6th carbon. Okay, so an inorganic phosphate group consists of a phosphorus atom doubly bound to an oxygen atom, like so. And then the phosphorus atom has 2 alcohol groups coming off it, like so. And then it also has an oxygen atom linked to it by a single bond, and this other oxygen atom has acquired another electron via ionic means, and therefore has a negative charge, like so. So this is the structure of an inorganic phosphate group. Now, basically, what we have done is we have linked a phosphate group onto this alcohol group. Yes, we didn't get it from an inorganic phosphate, we got it from an ATP molecule, but effectively what we have done is we've taken a phosphate group and linked it onto the alcohol group of the 6th carbon of a glucose molecule. Okay, and the logic behind this reaction is basically it's very similar to an ester link. Okay, so if you imagine for a moment that this isn't a phosphorus atom here, but is instead a carbon atom, then ignore the fact that we've got 5 bonds, which obviously doesn't make any sense because this is a phosphorus atom. But if you imagine it is a carbon atom and just look at this double bound to an oxygen and this alcohol group here, then basically we've got a carboxylic acid group there. Now carboxylic acid groups can link to alcohol groups via ester links. Okay, and what happens is you take the alcohol group off the carboxylic acid group, you take the hydrogen off the alcohol group, combine those together to make water, and then link the remaining oxygen to the carbon atom. And basically this can happen just the same for phosphate groups as it does for carboxylic acid groups, and that's what's happened here. This isn't now called an ester link, but it's called a phosphoester link. So that's what we've done. We've bound a phosphate group to the 6th alcohol, to the alcohol group coming off the 6th carbon of the glucose molecule via a phosphoester link. And this molecule that we've created is called, it's often referred to as glucose 1-phosphate. Obviously that isn't its rigorous name, because if we were doing it rigorously we'd have to talk about the optical isomerism, but when we're talking about glycolysis, everyone just calls this optical isomer of glucose, okay? So we will therefore call this glucose 1-phosphate in that same spirit. Okay, right. So we'll call it there for this video, and in the next video we'll continue the discussion of this pathway.